Hi, I'm Dhiyar Satnitu. This presentation is divided into three parts. First, I'll explain the problem and research gap using slides. Then I'll walk through the notebook and code. Finally, I'll demonstrate the system with both positive and negative test cases. Let's begin. Sepsis is a life-threatening response to infection. It accounts for about 20% of deaths globally and costs the US healthcare system around $24 billion each year. The key challenge is time. Every hour of delayed in antibiotic treatment reduces survival by about 7.6%. So early and accurate detection is critical. However, current tools are limited. Symptoms like fever, high heart rate, and low blood pressure are non-specific. Blood cultures take up to 72 hours, and role-based systems like SOFA produce very high false alarm rates, leading to alert fatigue where clinicians begin to ignore warnings. Although machine learning models report high performance, many of these results are inflated due to data leakage, which is the main issue addressed in this project. There are four main types of data leakage in existing systems. First, temporal leakage, where data from after sepsis onset is included in training. This causes the model to learn outcomes instead of early warning signals and can significantly inflate performance. Second, identity leakage, where the same patient appears in both training and test sets, allowing the model to memorize rather than generalize. Third, documentation leakage, which occurs when clinical notes are filtered using chart time instead of store time. This can include information that was not actually available at prediction time. And fourth, pre-processing leakage, where transformers like scaling are applied before splitting the dataset, allowing test data to influence training. This project eliminates all four types simultaneously. Looking at prior work, several gaps remain. We can see that Soil achieved a strong performance but did not control leakage. And Shashkumar used both structured and text but only partially addressed leakage and produced separate explanations for each modality. Bennett et al. Performed external validation but did not include clinical text. This project addresses three gaps: complete leakage prevention by design, unified explanation across modalities, and controlled experiments that quantifies how leakage affects performance. The system uses two input streams from mimic form. Structured EHR data is followed through an LSTM model to produce a probability score. Radiology notes are filtered using store time and processed using biochemical BERT to produce another probability. These two outputs are combined using a logistic regression meta model to generate the final sepsis risk score. The system also provides three levels of explanation: overall modality contribution, feature level importance from the listing, and key terms from the clinical text. Importantly, all explanations follow the same temporal constraints as the predictions. The LST model takes 18 hours, 18 hourly timestamps with 15 clinical features. It consists of two LSTM layers with 128 hidden units, followed by a layer normalization and fully connected layers to produce a probability output. Layer normalization is important not only for training stability but also for producing meaningful gradient based explanations. Additionally, a class weight of 40.6 is used to handle class imbalance, ensuring the model prioritizes detects sepsis cases rather than default into predicting no sepsis. Three experiments were conducted to validate the design. First, a window sensitivity analysis showed that shorter windows perform better, but an 18-hour window produces the best balance between performance and clinical relevance. Second, a controlled leakage experiment demonstrated that even small pipeline mistakes can inflate performance metrics, confirming the importance of strict controls. Third is an ablation study showed that adding clinical text through bioclinical blood improves performance by 13.5% compared to using structured data alone. The system we is developed using fast API server running locally with an average inference time of about 479 milliseconds. In the demo following, I will show four cases, a positive and a negative patient. So moving on to the code. This is the extraction notebook. In here, the entire pipeline is controlled by two values: OBS window list and spread horizon. The OBS window list is four candidate observation windows: 6, 12, 18, and 24 hours. And prediction horizon is fixed at 6 hours for every iteration. The key comment here is that the cohort is filtered using the largest window, which is 24 hours. So global minimum ICU becomes 30 hours, 24 plus 6. This means the exact same set of patients is eligible for all four window candidates. If I had filtered separately for each window, the 6-hour version would have had far more eligible patients than the 74-hour version, making the comparison completely unfair. In here, I build the ICU cohort after the BigQuery returns. Three filters are applied. Out time must be Out time must come after in time. LOS must be at least 30 hours, which is the global minimum ICU, and the loss is capped at 240 hours to remove extreme outlier stays. Then drop duplicates on stay ID, so each admission appears only once. Here, sepsis 3 labels from Mimic for pre-computer derived sepsis 3 table is extracted, and because uh, here the condition is SOFA score greater than or equal to 2 is suspected infection. I use this derived table rather than doing my own manual antibiotic keyword matching because the Mimic 4 team has already standardized the definition. The important line is drop duplicates with key equals first. A patient can have multiple suspected infection episodes in one stay, and I only want the earliest one. Using the latest onset would artificially give the model more prediction lead time. Moving on to radial nodes. The query pulls both chart and store time for every radial node. Chart time is when the clinician ordered the imaging. Store time is when the radiologist actually finished the report and it became available to the staff. The gap between those two times is typically 2 to 6 hours. If I filter on chart time, I include reports that were not yet written at the time of the prediction. A note ordered at 2 a.m. but finished at 6 a.m. would appear in the window that ends at 5 a.m. The clinician had not seen it. This is temporal leakage coming through the text modality. The fix is this line. Save time equals store time. This is a primary card. Chart time is only the fallback when store time is null. From this point on, every single downstream filter uses save time, never chart time detected. Here, this cell defines helper functions and feature configurations. Window features compute six statistics per feature per patient: least value, mean, minimum, maximum, and which is last minus first, and missingness rate. These become the flat feature vector used by the light GBM baseline model. Our aggregation converts raw timestamps measurements into an hourly grid by flowing chart time to the hour. This is the format the LSTM expects. Then, then FL limits. Heart rate is forward filled for only 2 hours. Lactate for 8 hours. Standard labs for like creatine for 24 hours. GCS for 4 hours. These limits are clinically motivated. If there is no heart rate reading for 12 hours, propagating the value forward would be clinically wrong. Beyond the limit, the value becomes missing. This is the main loop. I want to walk through specific sections. First, prediction window construction. For positive states, patients who develop sepsis, prediction time equals sepsis onset minus 6 hours. Window end equals prediction time. Window start Window start equals window end minus the OBS window. So for 18-hour configuration, we are using the 18 hours of data that end exactly 66 hours before the patient meets sepsis 3 criteria. For negative stays, patient who never develops sepsis, prediction time is the ICU midpoint, which is in time plus half the total stay duration. Not addition and not discharge, the midpoint. If we used admission time, patient would be at their most unstable, and that would bias the negative class to look more like sepsis. So the midpoint is neutral. Second, the leakage firewall. Every row data table is independently filtered for vitals, chart time greater than or equal to window start, and strictly less than window end. That strict less than or on the upper bound means nothing from the prediction moment itself or after it enters the window. The same pattern applies to the labs, GCS, vascularis, and ventilation. For nodes, save time strictly less than window end, not chart time, save time. This is the Stogard applied a second time. Third, the programmatic assertions. After the flood dataset is assembled, the pipeline asserts the window end is less than or equal to prediction time for every row. After the LSTM grid is built, it asserts the chart time is strictly less than prediction time for every row. If any row violates either of these, the notebook raises an exception and stops. The pipeline cannot silently continue with leaky data. This is what integrated leakage prevention looks like in practice. So this is the result that is generated, and that is the data extraction notebook. So this is the model notebook. The first thing that happens is loading data from the 18-hour window folder that the extraction notebook produced. Section 1.2 and 1.3 inspect the data, printing columns, names, label, distribution, and missingness rate. This confirms that the dataset looks as expected, and around 2.4% missing values missing because it's only drawn when clinically indicated, and vitals are near complete. Section 1.4 checks psychological ranges, heart rate, SpO2, temperature, mimics for pre-clean derived tables. Have already removed extreme outliers, so this should pass cleanly. And section 1.5 is leakage verification. Here is the first leakage check, even though the extraction notebook already asserted integrity. We check again here before any modeling fitting begins. The assert line checks that window end is less than or equal to prediction time across the entire loaded dataset. If someone had modified the paragraph files externally, this should catch it and the output should read. Check leakage passed. Here, section 2.1 is the data split, and here we are splitting on the patient identifier, not the stay identifier. One patient can have multiple ICU admissions, multiple stay IDs. If you split on stay ID, the same person appears in both training and test, and the model memorizes the physiology rather than learning patterns that generalize. That is the identity leakage. Splitting on subject ID means any given patient is in exactly one partition, training, validation, or test, never more than one. And section 3 is feature preprocessing. Section 3 handles feature preprocessing. The metadata columns are excluded first. stay ID, subject ID, prediction time, window boundaries, and any demographic columns. Everything remaining becomes the feature set. Then the standard scalar fit transform is called on the X-train only. Then transform, no fit, no val test. If you fit the scale on all the data, the test set statistics influence the training normalization. This is subtle but real leakage route. Section 4 is baseline models. Here we train a logistic regression and random forest and light GBM on the flat windowed features. Light GBM is the strongest baseline at AURC of 0.7 and AUPRC of 0.059. These are the numbers the LSTM needs to beat, and it does by a very large margin. Section 5 is the text model. Section 5 builds a text only baseline using TF and IDF and logistic regression on the radial nodes. Before any text is pre-processed and before text is processed, the store time guard is applied and nodes filtered where safe. Time is less than or equal to end to end. The TF IDF baseline achieves a URC of 0.76 and a UPRC of 0.07. The text technique exists, but it's weak on its own. It needs to be combined with structured EHR data to contribute meaningfully. Here we have the multimodal fusion of both these modalities, and it has an accuracy of 0.76 and a AUPRC of 0.076. Moving on to part 2, before that, section 13, which is uh, bootstrap confidence intervals. Here we define the bootstrap CLF function, 1000 resamples, drawing with replacement from the test set each time. The 2.5th and the 97.5th percentiles gives the 95% confidence interval. These apply to every model in the final charge table. Point estimates without the confidence intervals are not credible evaluation. The CI tells you how much uncertainty comes from having a finite test set. Moving on to part 2 section where we fuse LSTM with clinical build. Section A1 and A2 where we load the LSTM sequence and build tensors. Section A1 loads the LSTM sequence paragraph file, the hourly grid produced by the extraction book. Each row is 1 hour for one patient within the 15 feature column. Section A2 builds the 3D tensors. The feature list is the 15 clinical variables. SEQ lens equals OBS window and which is 18. The build tensor function iterates over the patient's sorted by chart time. The patient has exactly 17 rows, it is used directly. Patient if fewer it's zero palette at the front. If more it takes the most recent rows. The standard scaler is then fit on the training tensor, reshape from 3D to 2D. All patient hours flattened into rows, then reshape back to 3D. Val and test are transformed but never to fit the scale. Section A3 is the LSTM model and training. Here we define and train the sepsis LSTM. Two LSTM layers with 128 healing units. Batch first set to true, dropout of 0.3 between the layers. Layer normalized on the final hidden state, and then two fully connected layers down to a single unit output. Layer normalization matters beyond training stability. When the fast reversal runs gradient attribution at inference time, it backpropagates to this forward pass. Without layer normalization, the gradients vary widely across features and timestamp, and the attribution heat map becomes meaningless. With it, the gradients are well conditioned and the values are interpretable. The written hidden flag in the forward method, when set to true, the method returns the hidden state before the classification head. The server uses this extract the hidden state, then backpropagates to compute import multiple gradient decency without needing a surrogate model. For the training loop, three decisions to highlight. Post-weight is post-weight is set approximately 40.6, the ratio of negative to positives. This tells the loss function to penalize missepsis cases 40 times more heavily than a false alarm. Without this, the model converges to predict inosepsis for everything, which gives 97.6% accuracy with zero sensitivity. Cosine annealing LR decays the learning rate smoothly from 1.3 down to approximately 0 over 40 expos. Gradient clipping at 1.0 prevents exploding gradients. Best expo checkpointing is on validation AURC, not training loss. Training loss keeps falling past expo 20 as the model overfits. Validation AURC peaks earlier then plateaus. The checkpoint saves the weights from the peak and restores them after the loop finishes. Section A4 is clinical blood embeddings. Section A4 extracts bioclinical embeddings. The model uses ML sensor bioclinical pre-trained on PubMed abstracts and mimic three clinical notes. We never fine-tune it. We use it purely for CLS embedding extraction. Before a text is processed, the store time guard runs again. Nodes are filtered where save time is less than or equal to window and this is the third application of that guard, and leakage prevention should never depend on a single checkpoint. Then the last three nodes per patient window are selected, sorted by safety, and concatenated with the birds separated token between them. Patient without nodes get an empty string. For the actual embedding, each node is tokenized without concatenation, then splits into chunks of 15 token, 512 tokens, birds maximum context. The CLS tokens from each chunk is extracted and the chunks are mean pooled to give one 768 dimensional vector per patient. Now the two pass mean embedding strategy. This is how we handle the 75% of patients who have no node. And section 5 multimodal fusion. Section 5 builds the fusion. There are two approaches. The weighted fusion baseline combines the LSTM and BERT probabilities at a fixed ratio of 0.6 and zero point 0.4, no learning, and fixed rate regardless of how reliable each model is at for each patient. The metamodal fusion stacks both probabilities into two-column matrix and trains a logistic regression on the validation set outputs, not on the not not the training set outputs. Yes, the LSTM and BERT have already been trained on the training data. Their predictions on the same training data is overconfident. We memorize those patterns. If we train the meta model on those over predictions, we be learning to combine two corrupt signals. Training on validation output means the meta model learns on two genuinely out of sample estimates. And section 6 is verification, and A7 is results and calibration. Section 8 shows an ablation study, and section 15 is more leakage experiments. Part 3 runs OBS window sensor analysis, and part 4 of the notebook exports all the model artifacts. Now I will demonstrate the application. Here we can upload a patient CSV file, and the model runs. As you can see, we uploaded a patient with sepsis, and the model predicts 95.5% risk of sepsis. And this chart shows what features contributed most and what drive the most prediction. And here we can see the EHR features, and then we can see the explanation for the clinical notes. Now let's upload a negative test case, patient without sepsis. As you can see, the model correctly predicts that this patient does not have sepsis at a risk of 6.4%. And both models accurately predicts that the patient does not have sepsis. And the reason for this is shown in this explanation graphs. Now let's try that again with another patient. Here again we can see that both the models correctly produce, and the meta fusion model also correctly predicts that the patient does not have sepsis. Now let's try with another sepsis case. As you can see, the model also correctly predicts that the patient develops sepsis. And that's it for the demonstration of the application, and thank you.